Okay, welcome back. We were here a few minutes ago. And what I want to do, well, I want to estimate this. I'm going to do it by using this equivalence that is real. And there's really two things I need to know for this, right? So this is, so the product of all of these things, and then this probability of being in this category. Well, I guess I can estimate the probability of being in the category pretty easily. I could just look at the training data and count what fraction's in the category. That seems easy. This one seems harder. It turns out not so bad. So what I'm looking at here is, okay, given that I'm in this category, so I have my data, I can look at all the things in category K, and I can think about, well, what kind of probability is there for each input value there? Well, I could do that if I make a few assumptions. One of the assumptions I have to make is that the categories are independent, and they might not be. But as always, this is, well, if I tell you that the value for x2 is 14, does that change your belief about what the value for x1 might be? If it does, they are not independent, and now this is maybe not going to work very well. But hey, we'll move on. And of course, you can see here, like, it's probably why this is a straight product, right? Like the probability of seeing the thing is just the product of all these independent probabilities. I kind of see how, like, even if I don't look at that algebra, I think I can see how that would fall out. That, well, let's assume that everything is independent. And then, well, if everything's independent and I want to know what's the probability of all these things happening at once, I just have to multiply them all together. That seems pretty reasonable to come out of some algebra. And then let's look at some data. Okay, so now I have data that I have two input features for. So like M is 2. I know two things about each data point, which I've plotted here as where it is in the X and Y axis. And then I've got 3 categories. So my, like, K or whatever it is can be up to 3 that are, I guess, red, green, and blue in my picture here, or red, green, and purple. I don't care what you call them. Okay, so the game that we want to play is, given that a new data point has arrived in the world, what color do I think it's going to be? I get a data point that is at -2, -10. It's down here. Well, I'm pretty sure that's going to be that should be colored blue, but how can I, calculate that? I don't want to just stare at a plot and guess. So I'm going to look at those numbers. What did I just say? -2 and -10. And I'm going to try to guess the probability distribution of the training data. If I can know, or I can guess the probability of the spam call coming in, just as I give that sentence, so if I can estimate the probability that way by knowing the underlying distribution or guessing the underlying distribution, well, underlying distributions, you can just calculate the probability. I'm going to guess they're normal. Lots of things are normally distributed. So, okay, take my training data, and for the training data, I can calculate the mean. I just know the formula. I can calculate the standard deviation. I know that formula too. And if I just assume it's normally distributed, then I know the probability distribution for each category. And then I can just calculate that. There's just some formula for it. Oh, that sounds great. Or I guess what I'm doing here, like this picture at least helps me understand what's going on. I'm going to just look at one thing at a time. So I'm going to look at the blue data points, and I'm going to look at the x-axis. And if I took those numbers, I would see this histogram that's up on the top, or the blue histogram, purple histogram that's up on the top. And then I say, okay, this is normally distributed. I've just decided to assume. If it was, what's the best normal distribution to fit that data? Well, calculate the mean, calculate the standard deviation, that normal distribution is the best fit. And then I do it, I turn my head sideways and I look at the y-axis. And I say, okay, if I look at this, what's the mean and standard deviation of a normal distribution that would look like that? Well, just calculate the mean and the standard deviation of the data, the training data, that one. And then when a new data point comes in, just look at what the value is of the normal curve on that spot. That's the probability of having that x value, y value, or whatever. And after all that story, as this is good, I mean, I feel like this is the way this whole course goes, right? I tell some long story and then I say, just import the thing and call it. Well, just import the thing and call it. There's a scikit-learn implementation of the naive Bayes classifier. I can create a model here. There's nothing to fill in here, or at least nothing you have to fill in here. So no hyperparameters. And then train it on the training data. And what I see is this, or I guess what the training process produces is this. So for like the linear regression, what it produced was a slope and intercept for each column. Here, it's producing a mean and a standard deviation for each pair, for each category and feature pair. So for column 1, that were plotted as the x values on that last slide, for the first category, that must be blue. So the first category, the mean was negative 1 point something and negative 9 point something. So negative 1 point something, negative 9 point. Yeah, the mean of the blue data points is down there. Sure, that's probably what I expect. And then for the probably the green category, the mean was there, and for the red category, the mean was there, or in whichever order. And the variance of the blue data points for each feature was that. And if I hand you a mean and a variance, I guess, yeah, they're variances. They're called sigma, but my comment says variance. Theta, where's sigma? Huh. The documentation doesn't mention anything about sigma, so I don't know. It's either variance or standard deviation. It knows. I'm sure the code knows. Well, okay then. If I hand you a data point that has the same like x and y values or whatever we're calling our features, then the visualization that's here is like for each like pixel, for each color, like, or for each pixel in the background, if that x and y value is fed into this model, what color would it color it? So what I'm hoping here is that like each point, so I have the validation data points being shown here. I hope that each data point is like on its own color background or whatever. So like this red data point that's hanging out over here, this one would be mispredicted. It is red, like I have a validation data point here that is red, but just given where it is, the model would have predicted, oh, that's probably going to be green. So it's wrong on that one, but it's right on most of them for this story. Or maybe this will help you. So this is like a cross section of this story at x equals 0. So like up this line, kind of in the vertical line in the middle of this plot. So if you start at a low y value, you would have predicted blue. And that's because these are the probability density functions of those three normal distributions that are kind of inferred from the training data. So yeah, for small y values, I have this normal distribution is the highest one, the blue one, category 0, I suppose. And then, okay, like we get this crossover point where, and it's at negative 6 point something, and you can see it happening here. Like it's the same crossover here where on the next slide, the red curve becomes the higher one, while then category red starts winning. That's the one that's predicted for a little while. And then category green takes over for larger y values. I'm I keep thinking there's some 3D plot I could draw, but like there is a 3D plot here, right? I could draw the like two-dimensional normal curve, the mountain shape in the middle of a plane that would describe the probability of being in category green, and then there's a red one and a blue one, and whichever one of those mountains is the tallest at any point, that's what the prediction is, and that's what color the background is. My matplotlib is not good enough to produce that plot, and also I'm not convinced I could ever make it actually visible, but there's a cross section of it that looks like that. Okay, so I have that whole story to tell, and the story is, of course, how you kind of can guess, right? I think that this is going to be a pretty good model on this data. Is it? Well, if I train on the training data and then come up with a score on the validation data, I get 0.959. That's a pretty good number. And if I compare the training data and the validation data, the scores are quite similar, so I'm not too concerned about overfitting. I don't know what I would do in this case. Like if I was overfitting on this data, I don't really have anything to do about it. There was no hyperparameters that I could play with, but well, I'm not overfitting, so I guess I am happy. Hooray. Let's do it again. So I have data here that can be ignored. And well, I'm using this make blobs function. It comes with scikit-learn just for like creating test data effectively. What's great, I need some test data. So I desire 100 data points. On the slides, I've been giving 2 features because I have a 2-dimensional screen and then I can plot it. Here I'm going to do 4 features. So there's 4 columns in my inputs and then 1 column of target, of my goal. I have 5 categories here, and I've included some stuff like I've set the random seed just so I can rerun my code and not get different results every time for the lecture. You shouldn't usually do this, but it's hard to give a lecture without. And then what's the standard deviation? So after all this story, what I effectively have is this, right? So for this data point, like, again, I'm just calling these features because it's what I have, but it's like I have a person and I measured their weight and height and like head size and their like VO2 max like respiratory thing, and that put them in a category 3 fitness level or whatever. Can I, or I guess when I had them actually run on a treadmill, their fitness level was a 3. So this is something I would like to be able to predict from those, right? So if I tell you a bunch of vital facts about a person that are easily measurable, can I predict the thing that's hard to measure, right? It's hard to get somebody to get on a treadmill to exhaustion or whatever, but it's easy to measure their height and weight and their body fat or something. We tell ourselves some story like that, except with fake data, because if I had that real data, I would use it on an assignment where it'd be way more fun. Okay, so we've measured things, and the goal is, given these, predict that. And it's a category. I know it looks like a number, but it's a category, right? It's not like there's no concept of there being a 2.99 that's close to 3. I'm either in category 3 or I'm not. So because I have 4-dimensional data, it becomes pretty hard to plot, but I've done this. I've picked 2 of the things and I've said, well, I have W, X, Y, and Z in my data set. I'll pick W and X and I get this. And I've colored the data by category. I'm not wild about that color map. Can I do this? Is that better? That's the only color map I know off the top of my head, so we're going to live with it. Okay, so is it possible to make this prediction? Like based on this plot, I'm not sure it is, but remember I've got 2 more like dimensions that I can't fit on my screen because I don't have a 5-dimensional Oh, so I don't have a 4-dimensional screen. University won't buy me one. But I could imagine like, okay, like if you're over here, if your W is relatively large, it seems like you're in category light blue. Maybe that's useful to notice. I can see some of those things. And like, it looks like the red and green values are kind of on top of each other, but they're not in this other axis. Oh, okay. Like, cool, right? So yeah, it really looks like purple and green are exactly the same. Oh, but they're very different for these other two features. So this happens, right? Like, even having like 4 things that I know about a data point might be pretty small. And I run out of dimensions on my screen to plot it and to visualize it effectively. There's other ways we can do this, but okay. I guess it's a good thing I don't have to do this by eye. It's a good thing I don't have to just stare at this and make up a rule, like, because we could have a rule, right? We could say if data Z is greater than 0 and data Y is greater than 0, then return purple. Else, if, and gross, right? Nobody wants to write that code. What I want to do is this. So I am going to separate, I know I just put them together into a data frame, but I'm going to separate the sort of inputs and the target. The features, I guess I should use the machine learning terminology. The features are W, X, Y, and Z. The things that I measured, the things that I know about the world, and the thing I want to predict is the target, Y. I'm going to do a test train split as I always do, which is again like 2/3 of the data is going to, 3/4 of the data is going to turn into training. 1/4 is going to be held back as validation data. And then train on the training data. I'll include the validation score here just because it makes me feel better. Oh, interesting. Okay, so test train split is random. There is randomness happening there. So my guess is, because I really, really don't think I'm overfitting here, it could be I don't have enough data and just the amount of data is such that I'm really delicate, but it looks like I'm overfitting here, right? This number is a lot higher than that number. This now makes me nervous. One of the ways that you can deal with overfitting is having more data. Where'd that go? Okay, let's get some more data. It's really easy right now. Might narrow things in a little bit. Not too much though. Okay, well, my plot's a lot denser, I guess, because I have 3 times as much data. I'm not surprised. Interesting. So again, the test train split is random. All right, so I do expect that if I run these last few cells, a few more, like every time I run them, I will get a slightly different number. That is weird. It's weird how much these are moving around. It is what it is. You can't fight the math. But okay, I guess now I question, like, am I happy about this or not? Maybe one of the reasons I'm not happy about this is, like, maybe I don't meet the assumptions. Like I said back here somewhere, the features are independent. So if I tell you, like, if I'm thinking about a line in that table and I want to tell you, guess what the W is. Okay, and I tell you what the X is. If that changes your belief, then they're not independent. I think they are. Well, fundamentally in this case, I have a cheat, right? I can just look up what make blobs does. Is my data independent? Probably. Like I'm pretty willing to guess it is, even though probably doesn't say here. It does say Gaussian, so it is normally distributed, which is another assumption I made here. Now, in the case of a stats tool, if you start violating the assumptions, you have to think, oh, maybe this p-value isn't real and I can't look at it. I can still use the machine learning tool. I just kind of expect that if I don't meet those assumptions, that maybe I'm not going to get a very good result. Now, there's plenty of reasons to not get a good result. One of them is your task is impossible. And I think that's probably what I've done here. like I've added so much noise to this data. The blobs are so big that, yeah, they're just not separable. They're just totally on top of each other. And there's nothing, no clever math can do that. So I'm gonna turn down the standard deviation a bit, which I get to do in fake data. I'm gonna tighten up those blobs. And yeah, that's what I thought. So, okay. Like if you're in the case where like inputs like this, like, w equals 4 and x equals 16 and y equals this and z equals that, that is equally likely. Like I have training data where a data point like that is both red and green. Like I have red data points around there, I have green data points around that exact same spot. I kind of expect there's not much, no machine learning model is going to be able to separate those, because what's it going to use? Maybe what I have to do is go back and collect, I have to give it another feature. Maybe I have other data I can use that would be useful and would make a better prediction. Maybe I just have to accept that I'm only going to get close here. I'm never going to be perfect. I'll leave it this way. I'll leave it this way. Right. So the thing that I had here, where'd it go? Yes. Okay. Different data set. I have this other code up here. It generates square, or I guess, yeah, 4-dimensional cubes of data. So this data is not, I'll give it lots of data just so you can see the shapes. No question, this data is not normally distributed. I can tell you that right now. This is a uniform distribution within some range. These are boxes, not Gaussian blobs. So if that's the case, again, no exception gets thrown. I still have a valid model. In fact, in this case, I have a really good model, just because, again, I have not much randomness in this test data, and things are very nicely far apart. It doesn't take a lot of clever math to know that, oh, yeah, up here is green. So if you're in that part of the world, predict green. That's what's happening here. It's like I've just given this a really easy problem with this test data, and so it does really well on it. Okay, that's fine. That might mean that this is a good tool for the job. It might mean that there's a better tool for this job that I would like be a little more confident in, but let's come back to that. Well, maybe I'm gonna, where's my randomness come from? Here. Let's, like if things start overlapping in ways that are just don't separate in any nice and tidy way, yeah, I expect these scores to change. I don't expect these to be exactly the same. Yeah, it's just an accident of the randomness there. That'll happen. Okay, I guess I am happy now, or whatever. I maybe should have looked, right? I can plot, of course. I can just say, like, I'm going to look at only category 0 or whatever. And maybe I should ask myself, hey, do you believe you're meeting the premise of this tool? Well, that's easy enough. So I have my data. So if I only look at the data where the category is, I don't know, 2. So I only care about those data, or I'm only going to examine those data points. And then I'm only going to look at the X value. I probably should look at the other ones, but in the interest of time, that. And then I'm going to plot a histogram of that. Do I believe that to be a normal distribution? Probably not. What about the Z values? Are those normal? Probably not. Okay. So again, the machine learning police don't arrest me. And this doesn't even mean that's a very bad model. It just means that I'm now a little suspicious about a naive Bayes classifier being the right tool for the job here. Sorry, a Gaussian naive Bayes classifier, because I don't think they're Gaussian distributions. Something else I can do here is check like not only if it's wrong, but where is it wrong? And so like what I'm seeing here on this slide, that on the slides, category blue was nice and far away. And yeah, it's really good at the validation data and category 0. Every single one is correct. For category 1, which I think is green, I'd have to look. Okay, so this is, it always takes me a minute here. The recall is how many of them you find. So of all the green data points, how many are found? 94% of them. Of all the things that you say are green, how many of them were truly green? Of course, those are, well, easy to confuse. And it always takes me a second too. Maybe I'll see, maybe over here I'll see something interesting. I need predictions, don't I? Well, it's on the slide for exactly that reason. Yeah, so like I've learned something here for sure, right? Like I have learned that category 2 is easy, whichever one that is. It's really, this tool is really good at it. Like what can happen is like, you know, maybe I will see like 0.5s here because like category 3 and 4 are perfectly on top of each other and they're just impossible to separate, but the other ones are easy. That is useful information, I guess. Like maybe what I'm like campaigning for here is looking at the score, like looking at the validation score is good. No question. That's a very useful number to look at. Comparing it with the training score is useful. But there can be a lot more of a story to tell. And you know, with fake data, the game starts to end pretty quickly because I don't know anything truly about this data other than it's some blobs in a plot that I just drew. Maybe, you know, geez, I've never tried this. So like for the RGB color stuff, again, given a color, give me the color word that it goes with. Maybe there's confusion between like specific colors. Like maybe there are just people who have participated in the training data that are like blue-green colorblind and they confuse that. I don't know. Maybe I'd learn something if we looked at the data that way. So with this tool, with the Bayesian classifier, and maybe I should be careful to point out here. So we are using a naive Bayes classifier. So naive Bayes is do that Bayesian probability trick to exchange the conditional probability. The naive assumption is that within one category, the values are independent. So there's, you know, the X and Y values are independent of each other. If I just look at one category. The Gaussian naive Bayes classifier is assuming normal distributions. There's other naive Bayes classifiers that assume a different underlying probability distribution, but we're going to look at that one. Okay, so if I have all of those stories and I have estimated what those normal distributions are, well, normal distributions just have a probability. I just look. So not only can I look at these values and I can predict which is effectively in this case asking what is the highest probability, which category has the highest probability here. A naive Bayes classifier can also tell you the probability. So what is the probability in, you know, your estimation from the training data of being in each of these categories? So like this, well, this first data point, 2, -6. I should keep this open. 2, -6. It's right here. Right. So the first thing that I'm doing on that slide is right near this try-point where all 3 of those categories come together. So I guess I'm not surprised that the probabilities are all really close to 1/3. Right. So this is like, well, 0.3, 0.4, 0.3, because they're all times 10 to the -1. Okay. Like this one is slightly higher, so it won. Maybe this is interesting to me, right? Like I can certainly imagine problems where I don't just want, here is my prediction. I also want, well, who was the runner up or something like that. Like I can, with this tool, just because of the way it works and because that this probability distribution is known or at least estimated, I can do this. For this other one, 0, -3, 0, -3. It's near the green and red boundary. So it's definitely not in category blue, right? So it's the probability of being in category blue was estimated at times 10 to the -6. These ones are close to 0.5. One is slightly higher, so it won. But I can look at that, and that is in there. It's all part of the story of, you know, calculate the mean standard deviation, estimate the probability distribution. And the reason I'm going on about this is none of that's in the code, right? It's very easy to just have this code and say, oh yeah, data, right? Test, train, split, train on the training data, look at a validation score. And that is all the code you need. But knowing if this is the right tool to choose or not, you need to have some of that story in your head. Do I think these are independent within categories? Do I think they're normally distributed? If they are, I have a pretty good idea that this might be a good tool for the job. And I can use all the stuff it has. One thing that I didn't mention in this equation, I've been kind of focusing on this one. It's like, oh, like you assume normal distribution and therefore you get this and you can estimate the probability of being in each category. You multiply them together and look at the biggest one. There's this thing hanging out too in this equation. What's the probability of being in category green? Just ignoring everything else. And that's also pretty easy to estimate. It's just count them. And so that happened here. What am I looking for here? This is what I want. I don't actually know if I can, there must be some way to get that out of here. Oh, sorry. I don't know why. In my slides, I look at sigma underscore. In the docs, it's var underscore, the variance. Either that has changed or sigma is there. I don't know. I don't usually look at it, so whatever. What I would really like to know is what's the probability of being in each. Probability of each class. Period is that. Okay, what did we get? Unsurprisingly, each one of my 5 categories is right around 0.2 probability because my training data is balanced. So what this is saying is in the training data, 0.218666 is the fraction of points that were in category 0. It estimated by looking at the training data and doing the very obvious thing of saying, well, it looks like about a fifth is in this category. And if those weren't balanced, okay, then it would have something else. Here's one where it isn't balanced. And this can happen, like it's all easy to create sample data, right? And have everything be perfectly balanced. Real data often looks like this, right? Like, what's the probability of this credit card transaction being fraudulent? Well, most of them are not. So in this one, I have there's the number of blue points and then 3 times as many green and the same number of red. Okay, fine. Maybe I know something about my data. And I can say that, and it was up here, I saw it go by. I can say, here's what I think the probability is of being in each category, because maybe the training data is not quite representative of it. Maybe the training data, just because of the way I did the sampling or the experiment or whatever, I have more blue data points than there should be. In the real world, the blue data points are much more heavily represented or something. I can totally see this happening if I was doing like the credit card fraud thing. I would want to train with relatively more fraudulent credit card transactions than natural because it's, I don't know, what's the number? Like 1 in 1,000, 1 in a million. Probably I would overrepresent them in my training data because I just got to get moving and I want the thing to see what fraudulent credit card transactions look like. But if my data doesn't match the reality, I'm going to make bad predictions. Long story short, you can say, like, again, the default thing being count the training data, like count the number of data points in each category in the training data, use those as a probability of being in the category. That's a totally good default and it totally makes sense. But again, I think I can tell that story where if this was fraudulent credit card transactions, then I would end up saying like, okay, look, I know my training data really overrepresents those, but in reality, this is only like, it's a very unlikely thing to happen. And then these are, well, presumably I have to make these add up to 1. And I think I have 5 categories. So, dang, I'm off anyway. This isn't fun for anybody. Anyway, I would do something like that. I don't know that we're going to have to do it in this course, but this is just another one of those cases of like, you know, maybe you have to know these options. And the reason this option is there is because of that formula I had on the slides. Sure, right. Just so you know. In this case, you know, if I fiddle with the priors to make them not meet the data, I get a slightly worse result. I guess I shouldn't be surprised. If I let them match the data, it's a little bit better. In this case, I'm assuming my data is representative of the real world. And so matching the data is good. Again, depends what I'm doing. I want to think probably about, again, what's my data? What's the reality? What kind of prediction am I making? And I can have a look. Almost certainly default is fine, right? Have a look. If your training data is representative of the world, hooray. I guess there's a question, like for that red, green, blue colors to color words problem, you know, is the training data representative? I don't know. Even though I collected the training data with past classes, I don't know. I made some code that produced a random color on a web thing and had 11 buttons below it. I don't know. I guess we'll say that the data is representative of random colors. I did my best. Hope it was valid. Okay. Another reason I wanted to talk about all of those things, again, independent, normal distribution, etc., is, like I said, it's a way to predict that you're about to go wrong. So over in this example where I had the rectangles or hypercubes or whatever, they are not normally distributed, but they are independent. I know they're independent because I can see it right up there in the code, but I also kind of looked and I thought about it and I thought, yeah, those seem independent. So I have one assumption met, but the other one's not. And it happens to be, I get reasonably decent. Scores there. Maybe if I chose a different model, I would get a slightly better score. But knowing that I didn't meet the assumptions kind of made me stop and think. I've got some more serious examples here where things go wrong. This is also totally valid data, right? So there's also a scikit-learn make moons function that generates data exactly like this. So this is 2 features because I have a 2-dimensional plot. Well, I promise there's only 2 features and I plotted them in 2 dimensions. It's not like there's other variables that I'm not showing you. Okay. If I look at just the blue points and just their y value, are they normally distributed? Well, probably not. I could draw a histogram. I don't think I need to. If I look at just the red points and just the x values, are they normally distributed? Probably not. Um, Also, are they independent? Well, no, they're not. So again, the game for independence is I have my eye on a specific red point. Guess the Y value. Okay, you got your guess? Okay, now the X value of that red dot is 0.7. Now, do you know something more about the Y value? Yeah, of course you do, because you know it's right here somewhere. Before, you knew it was here somewhere. Now you know it's here somewhere. Okay, so they're neither independent nor normal. So yeah, I guess I kind of expect this, right? I kind of would imagine that given that story, the Gaussian naive Bayes classifier is not going to do a great job. And once again, the visualization here is the background color is what would be predicted at that point. The data points are the validation points. And yeah, well, actually, if I only looked at the score here, I don't have the score in the slides, but I think the score is pretty good, right? Almost all, like all but a couple of my validation points are on the correct color background. And of course, the score is literally just that fraction. What fraction of the validation points are on the would have the right prediction made for them? So I bet the score is actually pretty good, even though this model is crazy for this data. Okay, this is just the wrong tool for the job, right? The naive Bayes classifier just is not, like, it can't produce that like S-shaped decision boundary that it needs. Okay, I need a different tool. We're gonna have to wait till well, we're gonna have to be next week for that. This data, once again, it is no, again, I promise, normal. There's normal distributions here. The X and the Y for both the red and the blue, all beautifully normally distributed. I know because I created the data. What they're not is independent, right? Again, looking at a blue point, guess the Y value. Okay, and if I tell you the X value, it's going to make your guess better. Not independent. All right, well, I could, again, no exception is thrown. The police do not come and arrest me. I can just shove that data in and get this is a probably relatively low score. But this is another case where I can do a transformation. And we did it in the stats part of the course for to try to make things look normal. Here, I can actually do it to try to make things independent. So the story that I'm going to tell here is, well, what if I do this? I'm going to keep the Y value unchanged, and I'm going to throw away the old X value, and I'm going to replace it with this. In other words, keep the Y value unchanged. My new X value is going to be old X value minus Y value, and do that. So I'm going to do this transformation on my data. I'm going to take the old two-column data set, and I'm going to produce this new two-column data set. And every time I see data points, I'm going to slide them through that transformation. And what it's going to do is turn that scatter plot into that scatter plot. Now I'm getting somewhere. Now I have independent looking anyway. Looks like normal distributions for everybody. Again, all categories, category comma feature pairs look pretty normally distributed. I promise. Like if you don't look at this and immediately draw a histogram in your head, that's okay, but I promise. That Gaussian blob is exactly what independent and normally distributed look like. And I get a good result for the deal, right? I managed to, after the transformation, have data that is independent, normally distributed. And yeah, so I do expect the naive Bayes classifier to do a good job here. I've met all of its assumptions. The data has a nice little separation in there, so I can tease it apart. Cool. It could be that you don't meet the assumptions and you just get a good score anyway because the problem is really easy, but you got to be a little bit careful about that. So what did we learn? Well, what do I think we learned here? I think the machine learning of the mass media and the machine learning of the hype cycle implies that like, oh, you can just take any problem and shove machine learning at it and things will happen. And, kind of like if you have a powerful enough machine learning tool, like obviously the naive Bayes classifier is not the most powerful machine learning tool out there. Um, I think knowing your problem domain makes sense. Like, what the heck did I just see? I just saw an article. It was like, oh, was it a bank that had some kind of like insane chat bot? It's like, hey, I want to transfer some money to the other account. And sometimes it did the wrong thing because, yeah, of course, sometimes it does the wrong thing. What are you, stupid? These are not magic wands. Even if Sam Altman wants you to invest as if it is a magic wand, doesn't mean it's a magic wand. It does seem reasonable to say, okay, the machine learning tool is allowed to take one of these 3 actions, and then I'll have an if statement to decide if it's one of those 3 actions or not. That seems like maybe you could do some programming around it too, but that's another course. In order to make all this work, I needed to kind of understand the model a little bit. I need to at least have some idea of, okay, this kind of calculation is going to happen. Okay, so like if the data is going to look like this, it's going to be good. And if the data is going to look like that, it's going to be bad. I probably need to be able to do some of those things. Okay, this is a bad time to start a new classifier tool. But what do we have? We have one regressor, linear, and we have one classifier, naive Bayes, Gaussian naive Bayes. We can transform any of them. Like we can put any of them in a pipeline and we can do something to make our data make more sense and then apply the classifier or regressor. That's cool. But that's a good spot to stop for this week. So I'll see you on Friday for the quiz, right? Yeah, okay, I'm recording this lecture. Great. I don't know. Next week in lecture. See y'all.